Welcome back, everybody. So I'll continue on this part that is either boring or scary. So boring for those of you who already know this, scary maybe for others. Again, the spirit of what I'm doing here is just I want to make sure that nobody's left out if they might not have everything, and then we'll catch with all the rest, building on top of this. All right. So a list. So set map lists, set bag list. These are what computer scientists call abstract data types because they actually implement them physically on computers. But I'm giving you the mathematical view right here. So a bag is like a set where you add a number of occurrences for each member, and a list has the notion of an order. There is a first value, then a second value, then a third value. Mathematicians call it a sequence. That's something you can find written as a U, and then as a subscript U1, U2, U3, and so on. And so you can build a sequence like that. For example, if I connect to eDots, which is the ETH website for courses, then I see a list of U. So this is an example of a list, again, has an order. All right. Then there is a notion of a pair of two things. It's also called a tuple, but with just two elements. And in order to define a pair, I use this little cross in there. That's basically a Cartesian product. And it basically means that I have two sets A and B. The first element in the pair comes from the set A, and the second element comes from the set B, right? And I just build a new set that's called A Cartesian product B. That gives me the set of all the pairs. Why is it called Cartesian? Because of René Descartes, who was a mathematician, and actually the idea of the Cartesian product is the Cartesian coordinate, right? You have the x-axis, the y-axis, and if you do the Cartesian product between the set of real numbers and then again the set of real numbers, then you get the plane, right? So this is where it comes from. But here we are not doing it with real numbers, we're just doing it with for data. So it's going to be finite sets or maybe countable sets. All right, so here's an example of a pair where I have ETH Zurich and 2000, which is the second value, and that belongs to the Cartesian product of the set of strings and the set of natural integers, all right? Because ETH Zurich belongs to the set of strings and 20,000 belongs to the set of natural integers. So that's what we call a pair. So technically what we do when we do this is that we take a set A and a set B and we just combine them in all the ways we can, right? That's the Cartesian product. So if I have, let's say, 5 elements in A and 10 in B, how many do I have in the Cartesian product? 50, right? It's the product. So here 2 and 2, that's 4, 2 times 2. So it's the cardinality, that's what mathematicians call it, is the product of the two cardinalities, right? So 2 and 2 gives you 4 possible combinations. In previous years, I said it's associative because it's kind of a natural thing to do as a database scientist. But of course, there was a purist mathematician who said, no, it's not associative. So now I say associative, kind of. Because technically, when you do the Cartesian product and again the Cartesian product, you might have some tuples in a tuples. It's again the inception thing, right? A tuple in a tuple in a tuple. But technically for database people, when we do the Cartesian product many times, we flatten everything. So you have an example here. Yeah, if I have the Cartesian product like 3 times here with A, B, C, D, I don't consider that it's Cartesian product of A and B and then Cartesian product of C and D, right? I just flatten it all. So this is why I'm saying it's associative, kind of, right? You just build it in this way. All right. So here's an example of Cartesian product between the set of universities and the set of Booleans. And now I have my Cartesian product on the right. So you see everything is in order because I have 3 universities and 2 Booleans. 3 times 2 gives me 6. And I have 6 possibilities on the right. Everybody is following? Okay. Now, as I said, the notion of pair can be generalized to the notion of tuples with many, many elements and not just 2. And so you can actually do the Cartesian product of many, many, many different sets. And again, you flatten everything when you do that. So you just means that you have an element of each, right? So you have DALL-E that is a string, ETH Zurich that's another string, CB that's another string, and 1892 that is a natural integer. And now this tuple with 4 different values belongs to the Cartesian product of string, 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 natural integer. Now you might start distinguishing the concept of a row or a record right here, right? Because that starts looking like the row of a relational table. That's exactly the purpose of what we are doing. All right. What I need next in my toolbox before I can build a relational table is the concept, three things: function, partial function, and relation. So I also need to define this. So a function is something that maps elements from a set to elements of another set. So in that case, from A to B, so every element in A will be mapped to an element in B. So I can draw it with a rows like this, with the rows coming from A to B. And I have a few constraints there. For it to be a function, I need an arrow from every element of A. I cannot leave anybody out, and I can also not have two arrows from the same element in A, right? Then I have a function. But it's totally fine on the right side that I have two arrows arriving at the same element, and that I have elements that don't have any arrow arriving to them, right? It's only for A, for the starting set, the domain that I need exactly one arrow from every element. Mathematicians can constrain, of course, if you don't like two arrows arriving to the same place, then you say it has to be injective and you disallow that. Then you can say also it's surjective, and then you would disallow for any element in B to be left out. But this we won't need in the lecture. In terms of notation, you can say that this function f, so f is the thing that maps from A to B. The set of functions from A to B is denoted with a horizontal arrow like this, A arrow B. But some people, including me, prefer the power notation. So I love to write B to the power of A, right? But that might actually be scary to a few people. So I try to stick to having arrows rather than the power notation. All right. And if you want to say that an element is mapped to another element, then you're going to have an arrow like this, but with this vertical bar right here. So it says the green element here is mapped to the purple element. You write it in this way. Is that clear for everybody? Okay. So that's an example of function when I have a set of 4 universities and then 4 different cities. I have the University of Zurich and ETH, they're both in Zurich. So you see it's not injective. And then I have Frankfurt that has none of the universities on the left. So it's also not surjective. And that's it, right? That's my function from universities to cities. Next, the notion of partial function. Computer scientists call that map, but mathematicians call it a partial function. A partial function is the same as a function, except that some members on the left could be left out. For example, you see the orange element on the set A on the left is left out. It's not mapped to anywhere. That's why it's a partial function. And then you just add a little cross, a vertical or oblique, usually vertical, from A to B just to say that it's partial. And that means that it's not every element of A, but some element of A. Could be none, could be all, could be some, it doesn't really matter. And then you have a partial function. A function, of course, is always in particular a partial function, right? So a function is a specific kind of partial function that happens to have an arrow everywhere. And a partial function is a generalization of that doesn't need the arrows everywhere, starting from A. Okay, here's an example here where I have a set of strings on the left, a set of values on the right. And you see that it's not a function, but it's a partial function because the birth date is not mapped to anything, right? So that's why it's a partial function, but not a function. For whom is that clear? All right. Computer scientists call them maps, the partial functions. And maps, just like sets and lists and bags, are one of the most fundamental abstract data types that we love to implement in all kinds of programming languages with computers. All right. So I'm going to say map because I'm a computer scientist, and it's also much quicker to say map than partial function. So it's also shortening the sentences that I'm making. So I'll call it a map. And thirdly, the third thing I need is a relation. A relation is even more general than a partial function. The difference between a relation and a partial function is that now I'm totally fine if I have multiple arrows that might start from the left. So you see the orange element on A, the first one is mapped to 2 elements in B, the red one is mapped to 3, that's a relation, right? So basically in a relation, I can do whatever I want. I can map any number of elements in A to any number of elements in B, right? But the nice thing is that a relation can be expressed entirely with notations that I've already introduced before, because if you think of it, a relation is just a set of tuples. Every tuple is one of these black lines here. What is a black line? It's a pair, right? For example, I have a black line between orange and green, the first one on the top. That's a pair, orange-green. It's a pair. What is a pair? It's a member of the Cartesian product between A and B. So technically, this relation here that is characterized with all the black lines in the middle is nothing else than a subset of the Cartesian product between A and B. All right? For whom is that clear? All right, so a relation is a subset of the Cartesian product between the sets that you want the relation on. Okay, now it starts smelling like relational tables, right? Slowly, because relational, that's exactly the direction in which it's going. Just for completeness, some people, instead of saying it's a subset of the Cartesian product, they might say it's an element of the power set, which is exactly the same thing, except it sounds a bit fancier. But so you might see also this notation right there. This P like this just means the power set, which is the set of all subsets of the Cartesian product. Okay. This is a concrete example of a relation between a set of strings and a set of strings. So I have here a set of 4 strings and then a set of 4 strings. You can either consider that these are really just these 4 and just these 4, or you could consider it's really every time the set of all strings, but I'm only showing these 4 that are actually mapped and the others are not mapped anywhere, right? It doesn't really matter, it's just an example. So technically, I have a relation that is a subset of the Cartesian product between S and S. It's just basically meaning it's a set of pairs between S and S. So a relation between S and S. Okay, so that's mapping. In that case, I have universities on the left and cities on the right. That's kind of putting in a relation the universities and the cities. Okay. Now, there's other ways to look at relations. The way to look at it in that way is called extensional. Why? Because I'm explicitly listing my pairs. All the black lines here, they're explicitly listed on the screen. Right? So this is called an extensional definition, where you just give the list of pairs like this, and now it makes it even clearer why it's a subset of the Cartesian product. So here's an example where you don't use these fancy diagrams, but instead just list them. You have ETH Zurich, Zurich, ETH Zurich, Singapore, University of Zurich, Zurich, UCL, London, and so on. And again, that's the extensional definition of my relation. Now let's try to build on that. What if we take it to the next level? A relation not on 2 sets, but a relation on 3 sets. Now that might seem a bit more unusual for mathematicians because it's more common to define relations on 2 sets, but computer science, we love to generalize that, especially for databases. So this is why we also generalize this notion of subset of the Cartesian product to more sets. So what if I have 3 sets now, A, B, and C? Then I just list all of my tuples where the first element of each tuple is taken from A, the second one from B, and the third one from C. That gives me a list of tuples, which is an extensional definition of my relation between A, B, and C. Still following? Okay. And now I can generalize that not to just 2 and 3, but any number of sets. Now I'm using the notation D because D is like domain, because the database people, they call them domains. Every one of these is a domain. So I have domain 1, domain 2, domain 3, all the way to domain N. And then I take the Cartesian product of these. I take a subset. That's a list of tuples on these domains. And that's called an n-ary relation. This notion of binary, ternary, n-ary, it's something that computer scientists use when you know what a function is in a programming language, right? You call a function, it has a number of parameters, and n-ary means it has n parameters, right? So in that case, that's what it looks like. It's an n-ary relation. It's really just a set of tuples that are taken with the domains. The first tuple is in D1, the second is in D2, and the last one is in Dn. Okay. Now I can generalize, but I can also make it more specific, right? And this is something that with a mathematical background, I also love to do. What if we only have one domain? Actually, it works too. You can have a relation of a domain just alone, right? It's kind of boring, then it's just a subset of the set. But that's basically it, okay? Never underestimate this, because when you do mathematical proofs, you always need to worry about these particular cases. Like if you deal with vector spaces, you still need to the case where the vector space has a dimension of 0 if you want your theorem to be true. Who needs a vector space with dimension 0, right? But technically, for the math to work, you need to consider all of these cases. In fact, there is an anecdote on these things that, let me see if I correctly remember. I think it was a famous mathematician who did his PhD thesis on vector spaces of infinite dimensions whose unit ball is compact. I think that's, if I get it right, I meant that's about that. So all the infinite dimensional vector spaces with a compact unit ball. And he wrote his entire PhD on this with all kinds of theorems and so on and so on. And then a bit later, other mathematicians show that that doesn't exist. So there are no infinite dimensional vector spaces with a compact unit ball. I hope I got it right, but just to show you the particularities of mathematics, that it can really be fun. All right, but I have my tuples. That can be 2, that can be 3, that can be n, that can be 1, and that's all fine. Now, I have another angle to look at these tuples. Instead of an extensional definition, where I just list them, I can also view that differently as a predicate. It's equivalent. The predicate means that you can give me any tuples taken from A, B, and C, anything. And you give them to me, and then I'm going to answer, it's in there or it's not in there, true or false. That's what my PR function is doing. It's true if it belongs to my relation, it's false if it doesn't. The first one, see, if I say orange, yellow, orange, right there. So if I compute the predicate on this, it's true. Why? Because it's right there. This one, if I ask for orange, blue, orange, it's false because it's not in there. So it should be clear by now that if I define a relation by listing the tuples, or I define a relation by giving you this predicate PR, that is just some kind of black box that tells you true and false, that's the same, right? If you have the one, you can have the other, right? Well, at least for the purpose of the course, because again, there are things that you can show with infinite sets that it wouldn't be true. But for our purpose, because it's a finite number of items in the relation, or because it's countable, it's equivalent, right? If you give a predicate or if you list them. For whom is that clear? Okay. So here's an example with on 2 strings. So I now have this predicate, and basically the predicate ETH Zurich Zurich, given this relation, is going to be true or false? True, exactly, because it's in there. That's the first one. And what about ETH Zurich Lausanne? False, because it's not. Exactly. Okay, and I could do it the other way around. I just would have to do it with a brute force approach, right? I just list all of the possible tuples, and all of them that are true, I put them in the list, and that's it, right? Okay. Now that we have that, that's our toolbox, right? We built our toolbox. We have sets, lists, bags, maps, relations, Cartesian products, tuples, and so on and so on and so on. So now, what do we do with this? Well, if you look at this, this is a relational table. It kind of looks like this, right? Similarly, the visual of this looks very, very similar, right? So you could actually see that relational table as nothing else than a relation. Remember, what you have on the right is a relation. It's a subset of the Cartesian product. It's a list or a set of tuples in that case, set of tuples. So you could define your relational table as a set of tuples where every tuple is a row in the table. This here is the reason why we also call the records tuples. That's because of the math, because in mathematics, that would actually correspond to tuples in this way. Okay, so now if I go to the math, I can define a domain D as some set of values, not any set. Of course, it would be the ones that people usually use in a database, like integers, decimals, booleans, and so on. So it's a set of values, strings, integers, natural integers, have to be careful, natural integers, and decimals D, booleans B, and so on. I can also throw a few more that technically the mathematicians might not think of immediately, but actually, if you're working in a company, you do care about these things. It's the set of the dates, the set of the possible times, precise to the milliseconds, the set of sequences of bytes, and so on. So this feels very computer sciencey, but technically, we also have these kinds of sets when we use databases. Okay, so here's my first definition of a relational table. Actually, that's the textbook definition, one of the most early definitions of a relational table. A relational table is just a relation over domains, meaning a subset of the Cartesian products of the domains. That's it. That's what a relational table is. And that's also why we also call it a relation, because mathematically that is a relation over n domains. And again, because I show that a relation over n domains can be with the extensional definition given as just a set of tuples, then I get my set of records in this way. For whom is that crystal clear, this idea that we basically look at the table as a set of tuples, and that's the reason we can define it in this way? Who understands this formula? Okay, awesome. And you have exercises also to play a little bit with this that take it a bit to the next level, but that's pretty much it. So it wasn't that scary, right? Okay. So here's an example. If I have two columns, ETH Zurich, Zurich, so the university is a city, then I have string and string, my two columns, and that's it, right? If I write it like this, so that would be the math, and now I can rewrite this as a table, and that's basically a set of tuples, right? It's the set semantics right there, right? So the order of the tuples doesn't matter. It's just a set that is a subset of the Cartesian product. Okay, that's our first relational table as a mathematical relation over an S and S. Now, a record is just a tuple, right? So if I take now an element of my relation, it's a tuple, and it consists of elements that I call T1, T2, all the way to Tn. I'm using numbers because technically that's what we have. If you define a Cartesian product in mathematics, you are indexing the elements of your tuples with positive integers, right? 1, 2, 3, and so on. So this is why when you have a tuple T, you're going to call the elements in the tuple T1, T2, all the way to Tn. All right? So these are my tuples. This is a tuple. That's the same as a row, the same as a record, but mathematically a tuple. And T1 here would be ETH Zurich, and T2 would be Singapore. Okay? And note that if I want to have atomic integrity, T1, T2, these are all atomic values, scalars. These cannot be tables in there. Okay. In fact, this definition, defining a relational table as a mathematical relation over some domains, was Codd's first idea. This is the most ancient way of defining the relational model. But let's look at it now, given the requirements that I gave you earlier. Do you remember what I told you? We need a few things. We need, for example, the order of the attributes shouldn't matter. If we have set semantics, the order of the records shouldn't matter. Then we saw that I should be able to speak about relational integrity, atomic integrity, domain integrity, and so on and so on. Ideally, I would also like to be able to talk about sets of records, but also bags of records, list of records. These are all the requirements I had. So how did we do? What if we define a relational table in that way, and now we compare it with the requirements that I gave you earlier? So it's actually disappointing. That's why the little tear over there on the emoji. It's actually a little bit disappointing because there's a few flaws with this, a few problems. The first one is that in a Cartesian product, the order is important. I mean, imagine if you're using the GPS coordinates, right? It sends you somewhere, and imagine that you swap the latitude and the longitudes, you're going to have a problem, right? You're not going to be at the same place because the order of the coordinates is important. So if we define a relational table as a relation, then we really have the notion of a first tuple, a second tuple, and a third tuple, right? So here, we are not quite happy about that because we don't want the order to be important. And what's more, we don't have any names, we just have numbers. Who wants to have a relational tables with just numbers in there? You would surely prefer to have like first name, last name, birth date, and so on. So that's not kind of what we want, right? we would prefer to have names in there. So we have two problems. We have numbers, and on top of that, the order actually matters, right? That's an example here with university and city. But somehow that's how it is, right? So if you go to many database textbooks, they will give you this definition of a relational table. They will basically define it with a few attribute names and then a few domains, and then they define it, the table, they call it the extension of the table as the relation over the domains, right? Subset of the Cartesian product. With this definition right here, technically you fulfill domain integrity. Do you see why we fulfill domain integrity here? Could it be that I don't fulfill domain integrity with this definition? Yes? Exactly. So we start with domains. From the very beginning, we say this is a domain, this is a domain, this is a domain. So by definition, I have domain integrity here, right? Because of the way I define it. So this is by definition. The relational integrity, remember, it has exactly the same columns in every record. It's also by definition because I ask for all of the tuples that they have an element in every one of these domains, right? So we also have relational integrity. Atomic integrity, we might not have. Why? Because I didn't say anything about the domains. So technically, the domain could be integers or strings, but the domain could also be a set of tables, right? If I don't restrict this thing. So technically, the atomic integrity, I have some flexibility. I can enforce it or not enforce it. But if I want to drop the domain integrity and relational integrity, I can't really do that, right? So we don't have that much flexibility in there for NoSQL, right? So that's another problem. All right. So you see, domain integrity, it has to be by definition. Relational integrity has to be by definition, but atomic integrity depends on what you call a domain and what you don't call a domain, right? If you restrict the domains to atomic values, then you have atomic integrity. So you see between the order here that actually matters, the fact that we don't have attribute names, and the fact that we're kind of stuck here with domain integrity and relational integrity with no way of dropping it for NoSQL, that's kind of not really ideal, right? Can we do better than that, or can we have a second definition? And in fact, the answer is yes. And I'm going to go through another way using exactly the same toolbox that I've shown you. I'm not going to go through yet another half an hour introducing mathematical concepts. Don't worry, I'm going to just reuse them. But we'll go for a second definition, second way of defining a relational variable. Are you ready for it? Let's go for it. Okay. So let's now again focus for a moment on the attributes. What is an attribute? Because I didn't have them here, right? I just have numbers. So if I have attributes and I want to give them names, then technically an attribute is a string. It's an element of S. And here, for those who are bored, I'm giving you a fun fact, is that the set of strings, if you have theoretical computer science, it's called the monoid. It has a monoid structure because you can actually concatenate three strings with each other. And it turns out to be associative. It has a neutral element, which is the empty string, but it's not necessarily commutative. And you don't have the inverse, right? So this kind of structure is called the monoid, the way you assemble strings. Okay, parentheses with the fun fact closed. These are a few examples of attributes. I had to put one in there: name, first name, birthday, product ID, account ID, and so on. Technically, I could also have an attribute called ETH Zurich. You might say it doesn't make sense, right? But mathematically, I can have any string I want in there. So these are just all the attributes I can have. Now, I'm going to do things differently. Instead of taking my domains and taking a relation over them, I'm going to start bottom up. I'm going to talk about the records first. So what is a record? It's a map. A record is a map, mapping what to what, mapping strings to values. The strings are the attributes, so I'm mapping attributes to values. Remember, a map is a partial function. A partial function means we associate some strings, but not necessarily all of them, to values, right? So a record associates some strings, some attributes to values. with V being the set of all the values I accept. For whom is that clear? That's just a record. It's a row on my table. Now here's a representation of a record, right? That's a partial function. This one has 4 attributes that it maps to something, and all of the other strings, they are just not mapped to anything. That's fine because it's a partial function. Last is Einstein, first is Albert, physicist true, and year 1905. So you see everything on the left is a string. These are my attributes. And everything on the right, these are my values taken from my huge set V in there. That's a record, a map, a partial function. This is a visual. It's not exactly the same one, but just to give you a visual, remember, this is what a map is. I just have attributes on the left, and I have values on the right. And every attribute is associated with 0 or 1 value, but not more than 1. Now, it turns out that we computer scientists, even though, of course, we love math, we have discrete mathematics lectures in our bachelors and so on, but we kind of like to write it in this way too, which is a syntax called, does anybody know? JSON? Who heard of JSON as a syntax? This is JSON. So technically, if you know JSON, a map is technically a JSON object, right? This is something we see in big data for engineers, if you saw it. All right, so I can do it with a mathematic taste or with a computer sciencey taste like this, JSON, but I can also do even better than that and visually represent my record in this way with my 4 attributes. So I'm only putting the ones that are actually mapped somewhere. I'm just not writing the others. There would be too many of them that are not mapped anywhere. And then I have my 4 values. So last is Einstein, first is Albert, physics is true, year 1905. Bingo. The order here is irrelevant. Why? Because in a map, there is no order. If I show you this, there's no particular order of the arrows. There's arrows or not arrows between members, but there is no particular order in them. So it means that if I start swapping columns in there, last and first and so on, mathematically, it's still the same map, still the same object. For whom is that clear? A map is only defined by the way it associates strings to values, but there is no order. So here, we basically earned points with this, because now we no longer have the issue we had before, that with the relation definition, we had an order in the attributes. So here we marked a point. That's another example with university and CD. Now, let me continue. If I have one map, one partial function, one tuple, remember that a map maps some strings to a value, but not all of them. So I could look at those strings that are mapped somewhere, those that have an arrow from them, right? That's called the support of the record, the support of the map. The support of the map is the set of all of the strings on the left that are mapped somewhere, that have an arrow from them. In that case, the support has these 4, because these are the 4 that are mapped, right? So the support is just these 4, and it's a subset of the set of strings, right? There's a gigantic number of strings that are not in there, but 4 of them are in my support. I can call it, let me use as a notation support as a function call. So if I have a record that I call T, then the support of T is going to be H. So here, if T is that record, here, that map with these 4 associations, and H is the set of these 4 values on top, then the support of this map at the bottom is H at the top. Do you agree? Okay, why did I call it T? Because it's also called a tuple, even though mathematically doesn't make sense, but the computer scientists, they will just still call that a tuple as well. Anyway, you see the difference of culture, mathematics and computer science, that technically, if the mathematicians saw that we call a tuple what is actually a map in computer, some programming languages, they would probably not be happy about that. But it's actually wonderful to just be exposed to all of these scientific cultures. All right. So the support of my map is the set of the strings that go somewhere, that are associated to something. Now, so I defined my records as maps from strings to values. What about my relational table? Well, I'm going to take a level of indirection here. I'm not going to straight away give you the definition of a relational table. We're going to take an intermediate step, and I'm going to give you the definition of what I call a collection. Right? Then we'll worry about relational table. So it's simple because a collection is just a set of maps, right? So this is a map, this is a map, this is a map. These are three different maps. And the set of maps is a collection. So you see, this S going to V with the cross, that's the set of all the possible maps. So if I have a set of maps, then that's a subset of the set of all maps, right? So my collection is just a subset of all the set of all possible maps. So in that case, I have a collection of three maps, and I have a set of maps. For whom is that clear? Okay. It's easy to remember a set of maps, right? How did we do? Well, technically here, do I have relational integrity or do I not have relational integrity? Who thinks I do have it? Who thinks I don't? Okay, so I do because how can you see it? It's the same attributes everywhere. So I have relational integrity. Here I don't, because I don't have the same attributes everywhere. Is that also a collection? Well, technically yes, right? Because all I said is it's a set of maps. The maps, they can be anything. Maps is just something that maps strings to values. So the first one is a map, the second one is a map, the third one is a map. So this is a set of maps as well. Yes? The cross means partial. Yeah, if there was no arrow, that would force me to map all of the strings to a value. That would not even fit in any computer on this planet. Right, so the cross means partial. Normally, it should be vertical technically, but I didn't find any symbol that would have the vertical cross. But this means partial function. Okay, it's really a matter of convention because you might find in some communities the fact that a function technically could be partial. So some people do not enforce that a function has to map every element. And then they just call the domain of definition of the function the support, right? Yes. Yes. So let me just to be very clear, because that's such an important definition that I want this to be clear. This part right here, mapping S to V with the little cross, it means the set of all possible maps. So this here belongs to this here. This second map, that's also a map, it belongs in here. This one belongs in here, right? And the cross says, I don't have to map all strings. Here, I'm only mapping 4 of them. Here, I'm only mapping 4 of them. And here, I'm only mapping 4 of them, right? So this is why I have this little. So now, what is this? If I forget about this part, right? I only take S to V. S cross the row V would be the set of all possible maps you could ever imagine. And again, that wouldn't fit anywhere on our computers, even if we use the entire planet. That's just too gigantic. So it's just a mathematical construct. It's the beauty of mathematics. In math, we are able to do these things. So S cross the row V is the set of all possible maps you could ever imagine. So these are 3 of them. On the next slide, I have some others. So it's a gigantic set with every single possible map that could ever exist. And when I say that my collection is a subset of that, is that I don't require all of them, but some of them. So I have, in that case, just 3 maps that are in my collection. Does it make sense? Yeah? Yes? Yes, because the empty set is a subset of any set. Yeah, it's just mathematically. So C could be empty, and that's still a subset of the set of all maps. Mm-hmm. Technically, I could also have the collection that actually contains all possible maps, right? But it's only a theoretical thing. I can just wave my hand and say this exists. You will just not be able to put it on any computer, right? It's a pure mathematical thing, right? So a collection is a set of maps. Okay. All right, now this is also a collection because these 3 maps, they have just the same right as anybody else to be a map, right? They're just mapping a string, some strings to attributes. So these are also maps. So technically, this definition right here fulfills this, but also this. So it means that I don't have to have relational integrity with this definition. It's some additional thing that I can enforce, right? So I can add the constraint that I also want relational integrity. It's an additional constraint that I put on my collection, and I say, I also want my collection to have maps with all the same support, like this. Then I can paste them together as a table. So technically, this here is not sufficient to define a relational table. I need to add my 3 additional rules that I told you earlier. You have a question? So, Raisan, yes? That's a record. That's what we call a record. Every one of these is a record. So record, map from string to value, tuple, these are all the same thing, right? It's a row in a table. A set of records, yeah. Group would be a casual way of calling it, but so the mathematical term is set, but yes, that's exactly the idea, right? A collection is just a group of records or a set of records. If you say group, mathematicians will assume other things. So group technically has some operator that has a neutral element, associative, and so on. So this is why I'm careful, but technically, yes, the intuition is there, right? Okay. So basically, if I add the constraints that I want relational integrity and add that I also want the same support, then I'm 1/3 of the way towards a relational table, right? If I want to go 2/3 of the way, then I have my second rule, atomic integrity. This one's easy. I just need to make sure that V, when I define V, the set of values, I just want to make sure it only has atomic values. If I do that, I have atomic integrity. If I don't, then I don't have atomic integrity. That makes it easy to switch on and off, right? I can switch that on and off. I just can require that or not. This I can also switch on and off. I can say yes or no, I want the atomic values. And my third thing, I can also switch on and off. In my case, if I switch it on, then that actually works because you have all strings, all booleans, all integers. So in that case, it has domain integrity and I can put that in there. But if I want, I can also switch it off because you'll see if you actually don't require that it's the same domain for every column, then that would still be a collection. Because again, a collection is a set of any maps. There is no constraint. So basically, I won because I have a definition that fulfills all of my requirements, and I can switch on and off the 3 rules that I told you about relational, atomic, and domain integrity. All right, so before you go, I just want to make sure that you followed, and then I will let you go if my computer accepts to let you go. It seems to actually don't want you to go. Okay, so I'm just checking. This is my way, basically, of knowing should I slow down, should I accelerate? So it's just a way of getting a feeling of this. And then I adapt a little bit. Every year it can be different, right? Some years it might be too fast, some years it might be too slow. That looks good. So the 80 to 99%, that's kind of my sweet spot. This is where I like to be. And it's totally normal. I mean, it's awesome if people understand everything. It's also okay if you understood even less than half. Why? Because we're here. I'm here. The TAs are here to help you, and we will make sure that you understand. So do not worry, even if you didn't understand everything. You can read, you can do the exercises, and you'll see there are so many practical exercises that it will all make sense when you'll have the exercises, right? Everything will fall into place. All right. So thank you very much for attending. I hope you enjoy your meal, that you enjoy the exercises, which is pretty much about installing Docker and making sure that it works this week. Next week, we'll continue. I'll finish that, and I'll show you practically how to define these structures using the SQL language. Thank you very much. Enjoy your meal, and see you next week.